about Dropbox system design. So in this I will be basically covering about how a system like Dropbox can be designed, which is a distributed file sharing system in which you can upload large files, sync it across multiple clients, download it from each or any of the clients. So I'm going to discuss about how to basically create such a distributed system in which supports all of these capabilities. So let's just dive in. So let's just first try to ask the question, why do we actually need something like Dropbox or a cloud-based file storage system? So we basically need such systems for just three reasons, which are availability, scalability, and reliability. So just to give a brief overview about it, so we basically want to access our files whenever we want to from our any of the device. So we are not bound by a particular device on which our file is stored. The system should be scalable, that it should be able to support large files however we want, and it should be reliable. It should not be the case that we uploaded a file somewhere and it got destroyed. We are actually trying to switch to a cloud-based system for uploading our files because the other systems that we use, like hard drives, they are not that reliable. It can go corrupt anytime. So these are the basic things that we look for when we are choosing any cloud-based file sharing or file uploading system. Now we come to the basic requirements. What would this system basically support? So it should support basic upload and download. We should be able to share our files. We should be able to sync our files across multiple devices. These can be your laptops, mobile phones, and any other device. And there should be asset properties. Like we discussed, that it should be available, scalable, and reliable. So it is necessary for this kind of system to support the asset properties. Now we're coming to the design considerations. Now when we have to design such a system, what things should we actually think about? Now the first thing, that the basic thing of this design is the upload and download of files. Now these files could be of any size. It could be a 2 GB file also, it could be a 10 KB or 1 KB file also. So we should take this into the design consideration. So it just states that there can be large files. How big? It can be 2 GB, 4 GB files. Now how would we actually support upload of such a large file? So like suppose there is a client and there is a server, and you want to basically establish a connection between these two and upload such a large file. Now you cannot do that in a single API call. Now how would you do it? So this is the first thing that we have to think about. Now the second thing is that there will be a lot of writes and reads. It is possible that you have uploaded a text file which is stored on your desktop, and you are also constantly updating that text file. Now if you are updating that text file, it should automatically sync to the server so that you can access it from your multiple devices. Now the next thing that comes into our mind is the concurrent operations. Now suppose you have the files on all your devices. Now suppose you are updating the file from two different locations at the same time. Now how would you maintain the consistency in this case? How would you determine which is the right version? Also suppose that you are uploading multiple files from your system to this cloud-based system. Now in this also we have to consider, like, how would we support the uploading and downloading of multiple files over the API requests that we have, or whatever channel we have to communicate between the client and the server. Now before moving on to the design, we should first do a basic capacity estimation. So any system like Dropbox would have around 500 million users. It would have, a user can have like this, an average, suppose 200 files per user and a 100 KB file. Now this file is quite small, quite size. With the like as we move forward in our generation, the file sizes are increasing. Even an image is greater than this 100 KB. So this is just a file average just for the estimation part. So storage in this case is 10 petabytes, and number of files that we have to store is 100 billion. So this is huge amount of data that we have to store. So one thing that also comes into mind at this time is that how would we store this large amount of data? Where would we store it? So we have to take that into consideration also. Now let's come into the big issues that we see, which we can run into while designing such a system. Now, first is how to store such huge data. Like, where will you store? Like in your laptops or computers that you see, you have 2 TB of RAM or 4 TBs of RAM. But here we are talking about 10 petabytes. Obviously, now when you're designing a server distributed system, you won't have just one server. You would have multiple servers. So these files would be stored on multiple servers. Now, in that also, you have to think that if your file is stored across multiple servers, there should be replications of those files also. For example, if one of your server goes down, the user should not be impacted. So you have to think about these things, that you have to store a huge amount of data and even store replicated copies of those data on multiple servers. Definitely you are not going to use just one single server. Now, how to support uploading of large files. So now suppose I upload a 10 GB file. How would you upload this 10 GB file from client to server? You cannot do it in a single API call. How would you use? You basically would obviously use a streaming API. A streaming API to basically maintain the connection between the client and the server while the upload is happening. But still, if you are uploading a 10 GB file and suppose your internet connection is, a user's internet connection is just supporting, let's say, even 15 MB per second, still this would have to maintain a connection for such a large amount of time. And suppose after uploading 80% of the file, the upload stops due to some reason, the internet drops, then you would have to resume such uploading of the complete file again. So you have to think about these issues also, so that these issues do not come when you are creating this system. Now the next thing which comes into mind is how to handle the concurrent operations. These are the operations which I discussed earlier also, like supporting upload of the same file from multiple devices or supporting upload of multiple files from the same device. So these are the two things which can happen at in this kind of system. Now let's come to the solution part. Now the first thing that we have to store, the first problem that we have, where to store data and what are the different types of data that we are dealing with. So the two different types of data that we would be dealing is the metadata. So we also need the metadata. For example, someone uploads a file. We also need the metadata. What was the file name? What was the file size? These kind of things. Also, that we are trying to prevent the duplication of files. If we want to prevent, we also need to store the hash of the file. So this is something which we need, and for this we will need a metadata database. Now next is the files themselves. Now where would you store these files? Now when someone is just basically designing the system, we have a lot of things available to us, like you can use AWS S3 and all those kinds of things when you actually are building the system. But suppose these were not available, you have to store the files. Where would you store them? Obviously at the back end, these would be stored at some location on a server on a hard drive itself. But still you have to manage where the files are stored, also manage the replication of those files, handling that whenever that these files should be available at all the times and they should be reliable. So if a person has uploaded a file once, it should not be the case that the file gets deleted at some later time. So you can build a system like S3 that you would have to build, or you can use a managed solutions which exist in the current market right now. Now, another question which comes to while storing these files, would you store the complete file itself together like as a one single file? So like I discussed before, like we cannot upload a one big huge file. It can cause a lot of problems. So basically what would you have to do? You would have to chunk the files into smaller pieces. Now if you are chunking the file into smaller pieces, you would also have to store it in that way. Or what you would have to do, you would have to combine those chunks into one file and then store it, which again can cause a lot of issues. So therefore we would go by storing the chunks of the large file. So we can take the chunk size to be anything, like suppose we take it as 4 KB as the chunk size of the files we would be storing. And these chunks should be stored on multiple servers, definitely, because we want to be reliable. If one of our servers goes down, we should be able to provide the file to the user. If you don't want to manage this yourself, like I discussed, you can use the managed solution like AWS S3. Now, for this metadata, we can use a SQL database or a new SQL database in which we will store this kind of information. Now, which database would you choose? That we'll discuss in some time. But these are the two types of data that we have to store. Now, as we just discussed about that we would be storing the chunks, we would also be uploading in the chunks. So you would have gotten the idea that who will basically do the chunking of this file. So we have a big file, who will chunk it into small pieces. So this, and when will this chunking happen? So we have to do this before upload only, because suppose after the upload we do the chunking, then that causes the same issues that I discussed with uploading a large file. So this chunking has to happen on your desktop, on your client application. So this also would help to support parallelization. So suppose you have a 10 GB file, you broke it down into 4 KB small file sizes. You can upload all these files together as separate chunks and create a metadata entry for each chunk, and this can help to support parallelization. Now we come to the basic high level design of this system, like how would this system look like. So this system, as we discussed, would have a client application. It can be a desktop or a mobile, any application. Then it would have a server, block server, which would basically store the blobs or the blocks of files, and this is the cloud storage that we would be using. You can use, like, as this cloud storage, you can design your own solution, or basically you can use, as I discussed, the AWS solutions. Next, we can use the metadata server. This would be updating the data in the metadata database. Now this metadata database can be SQL, no SQL, we will discuss that. And there should be a synchronization server. Now why this synchronization server is needed, we'll talk about this, but this is needed, which will communicate between the client and this metadata database, and also this metadata server basically. So it will not directly interact with the metadata database, it will fetch the information through the metadata server. Now what are the client responsibilities here? The client responsibilities, the basic ones, are uploading, downloading, and the chunking part, which I discussed. It also has the responsibility to detect changes. Now suppose you are making a file change on your laptop, you should be able to know on your mobile application that there has been some change made in the file, so that you can view that updated file rather than viewing that old version. So each client by I mean that each desktop, mobile, any app that you are using should be able to detect these changes and then sync these changes to the server, and that's where this synchronization server comes into picture. So whenever a change happens at any of the client, it will sync the changes to the server, and it will update the metadata database through the metadata server. Now, the third thing that the client has to handle is the handle conflict. Now, there are multiple devices updating the file, one single file at the same time. The client should be able to handle this conflict with the help of the synchronization service. Like if one change has been made, how to handle the multiple updates on the same file. Now, this becomes kind of like a Google Docs kind of system also, where you are updating the same doc from multiple places. So you would have to think of some algorithm which would help you to prevent this prevent any inconsistency, and so that you can handle the concurrent updates that are happening between different clients on the same file. Now another question that comes in the mind is, should we keep the copy of metadata with the client? Now, keeping the copy of metadata means that the file metadata that we have should, like all the files that are there on that particular device, should we keep the metadata about them on the client also? So what happens if we don't keep the metadata? So every time when a file updates, the client would have to fetch the data from the metadata server and then basically do an update. So basically it involves two operations. One is to basically get the data and then update the data. So we want to prevent this two calls and just make it in one call. So for that, we would also have to maintain the metadata on the client itself also, apart from just maintaining it on the metadata database. So this would help us save the round trip. Now, how clients remain in sync with other, like the problem that we just discussed. So what basically clients can do, they can ask the server periodically. Now this will waste a lot of resources and also cause a lot of inconsistency issues. For example, there are two clients that are updating the same file at some time, and these are updating in the server. Now when this client updates the file, it gets updated in the server, but this client still does not know that the file has been updated. It gets to know when it does the periodic ask from this server that has the file been updated or not. So this can induce a delay, and it could prevent keeping the file in a consistent state. So to solve this issue, what we can do is HTTP long polling comes into play. Now what this HTTP long polling does is, the client requests the status of like what has been changed in the file. The server holds the request open and waits. So instead of just terminating the connection between the client and the server once it has asked, it keeps the request open and waits, and then once the status of the file or any there is change in the metadata, it then responds back. So this helps to reduce a number of resources. Also, we are utilizing a lot of resources in this, also keeping the connections open, but this is necessary to avoid this delay that was happening before if we do not keep this connection open and ask the server periodically. Now, so as we discussed, the client has 4 parts. It should have a chunker, which would chunk the file. They should have an indexer. This would update the internal metadata. It should have a database to store this internal metadata whenever a file is updated, and there should be a watcher which would be always looking for updates and keep the connection open with the server. Now we come to the metadata question: which database should we use? Should we go with the SQL database or should we go with the NoSQL database? Now, if we go suppose with the NoSQL database, the NoSQL database is not ACID. By that I mean there are multiple clients which are updating the same file at the same time, and it is possible that the metadata is also being updated by the multiple clients. Now NoSQL is not ACID. By that I mean it can lead to an inconsistent state. So to maintain a consistent state, you would have to take logs on this database, NoSQL database, and that would be the job of the synchronization service. So this can cause some issues because we have to take logs, which is never a good decision in any design. Like sometimes it becomes necessary, but it also comes with a lot of constraints, performance constraints, which you want to avoid. So instead of that, we can go with the SQL. So SQL database, but that also comes with a lot of issues, that vertical scaling issues can be there with this SQL database. So we would have to shard our data, or we would have to do partitioning. For sharding and partitioning, what it means, I would not go into the details. Basically, you can take it as we would have to basically separate our data into multiple tables, so that there is not one single table containing all the data handling updates. So that can be one of the reason why SQL also does not suits. Now we can weigh the pros and cons and can decide, but just to keep it simple for today, let's just go with the SQL database because it is consistent, and each update happens in a form of a transaction, which keeps it in a consistent state. Now we would have to partition this database. We can do different types of partitioning techniques we can use. We can do vertical partitioning. This means suppose there are 10 servers in 10 different geolocations. Each server updates only the database of their particular location. Then there can be range based. So this range based can be on the basis of name of the file. For example, a file starts with A, another file starts with B. Then we kind of suppose on one partition we store the data from A to J, and keep on going like this. Then the next would be hashed based. So now as we also want to prevent Now we also want to prevent duplication of the files. For that we would need to maintain the hashes of the file also. So what we would have to do is go with the uh, keep the hashes of the files and then distribute the files according on the basis of their hashes. For example, the hashes a to like a particular 1 to 10 hashes are stored in one particular database, and so on. Now we come to this sync service. What this sync service would do, it would have to transmit to each of the client that something has changed. Now what would it transmit? Like it should transmit the complete new file. That would cause a lot of issues. Or another thing would be it can transport complete chunk which has been updated. So that would also cause a lot of information to be shared on each of the update, which is not necessary. What it can do, it just takes the diff of the old file and the new file and just updates all the clients and the server. So with this synchronization service, it would have the job of transmitting the diff and also calculating the difference. Now this client is always in contact with the synchronization service. Whatever updates happen on the client, it updates the synchronization service, it takes the diff and transports it to the server and other clients. Now how would this, there are multiple clients, so how would these clients interact with this synchronization service? How would they interact? So to interact with the synchronization service, we can go with two approaches. That for each update we do an API call to this service and make an update. Now suppose this API call fails, or there are multiple updates which are happening every second. So there are multiple API calls that we have to do. So how do we and there are multiple clients also. So each of the client making multiple API calls. So suppose hundreds or thousands of updates are happening. This synchronization service would have to maintain a lot of API connections. So how do we tackle this problem? So we tackle this problem with the help of a message queue. So what would this do? That every client which has to update, it will just put the update information in this queue, and then synchronization service can just poll this queue in the order of events and then keep on updating the system or the file changes that happen. Now finally we come to the storage system. Now the storage system would have to store the file, handle the updates also. Now suppose there are multiple files that have been uploaded and each file has been chunked. So suppose there is a big file and it has been broken down into small chunks. Now suppose there is an update in this file. Now if there is an update in this file, what would it have to do? It would have to just update the complete old file and put the new file into place. That would require a lot of resources. How can we reduce this? We can reduce this by just updating the chunk. Now this storage system should be able to find the chunk which has been updated. So this client should also send this information that this chunk has been updated. Now what the storage system has to do, it just has to check this chunk which has been updated and just update that chunk and keep the rest of them as it is. So this is how the storage system should be able to function. And this storage system is also responsible for storing the files in whatever system, be it a cloud-based storage system or be it a system designed by you, which is specifically for storage. We will not go into those details, like how would you design a particular storage system which can support storing a lot of files. So that is another system design in itself. So basically you have to see how would you support replication of these files, maintain consistency, basically support all the asset properties while keeping proper security and all these things in mind. Now we also have to check for the duplicates, like I said. So what would we have to do? We would have to keep the hash of each chunk that we have, and whenever suppose a person tries to upload a similar file, a same file, we can just match the hash and find out. It would also help in determining the update. So if the hash of a particular chunk gets updated, we know that this chunk has been updated and we can make the required updates in the storage database and also the metadata database. So that's how you would basically design a complete storage system, and it would support all of these capabilities. Uh, it would support all of these capabilities. So I hope that gave you a lot of new information which you did not have already. Do let me know if you have any questions on this. There are still a lot of things that can be covered in this, but that can be covered in some other videos. And I think that's all for today.